Hello everyone. Today we are excited to present our work on photolithography overlay map generation using an implicit knowledge distillation diffusion transformer. Photolithography relies on advanced optics and precise motion control. It begins with anamorphic optics, which increase the numerical aperture and enable higher resolution. Faster stages ensure high productivity, with the reticle stage reaching high acceleration. This precision makes it possible to achieve sub-nanometer overlay accuracy. Finally, the exposure process projects patterns onto the wafer, building integrated circuits layer by layer. These demanding requirements highlight the importance of accurate overlay map generation. Current layer overlay map prediction is a multimodal problem. It requires considering which exposure tool is used for exposure, along with the corresponding tool logs, which are text data. It also involves exposure chuck IDs and reticle IDs, which are categorical data. Finally, it must take into account pre-layer overlay maps, which are image data. Our proposed prediction model consists of four main components: a teacher encoder, a student encoder, a student decoder, and a discriminator. The complete image is first processed by the teacher DIT encoder, which embeds it into a token representation ZT. Meanwhile, visible patches from a masked image are passed through the student DIT encoder, producing token ZH. The invisible patches are then inserted into ZH, and the combined tokens are fed into the student DIT decoder to perform two tasks: denoising and reconstruction. In addition, multimodal information, such as labels, text logs, and pre-layer overlay maps, is encoded by pre-trained text and image encoders. Their representative embedding tokens serve as conditional guidance for the teacher encoder, the student encoder, and the student decoder. To ensure that the student encoder learns capabilities comparable to the teacher encoder, we introduce a discriminator as an implicit guide. While the teacher encoder has access to all patches, the student encoder only observes a subset of unmasked patches. Our implicit guidance mechanism helps the student DIT model learn to generate outputs as effectively as the teacher, even from limited visible information. This design significantly reduces the DIT model size, making it more efficient and suitable for deployment on edge devices. Next, I will introduce another key contribution of this paper: gated cross-attention for diffusion transformers. The student DIT encoder takes noised latent patches, together with text labels, images, and time step information, and embeds them into tokens. These tokens are processed through transformer layers, where operations, such as patch embedding and layer normalization, help stabilize training and improve representation quality. The encoded tokens are then passed to the student DIT decoder, which performs both denoising and reconstruction. On the other hand, the teacher DIT encoder receives the full input, including all patches, labels, images, and time step information. After patchify and embedding operations, it produces a complete representation, serving as a strong reference for guiding the student encoder. Inside the encoder, we incorporate a gated cross-attention mechanism. Vision tokens interact with conditional embeddings through multi-head cross-attention, while the TAN gating function adaptively regulates the information flow. This design enables the model to effectively balance visual features with conditional guidance, leading to more robust and accurate representations. Here we show the visualization results under different conditions. Compared with MDT, mask DIT, and SDDIT, our proposed IKDDiT produces overlay maps that are visually much closer to the ground truth. You can see that the other methods either lose fine details or generate noticeable artifacts, while IKDDiT preserves both structure and consistency. This demonstrates the advantage of our implicit knowledge distillation design. We compare the training efficiency across different models. IKDDiT converges faster and achieves lower loss than DIT, MDT, mask DIT, and IKDDiT. For small, base, and extra-large versions, IKDDiT consistently shows stable convergence and lower errors, making the training both more efficient and more robust. Here we present some representative results. The inputs include equipment logs, IDs, and labels, which are combined with pre-layer overlay information. From these multimodal inputs, our model generates overlay maps that capture the structural patterns and error distributions effectively. As you can see, the generated results closely match real process variations, showing that our proposed model can generalize well across different conditions. This concludes our presentation. Thank you for watching, and we look forward to sharing more at ICCV 2025. For more details, please feel free to scan the QR code or contact us directly.